Okay, now one of the things that you can see is that Schrodinger picture states do not evolve in time, but Heisenberg picture states do evolve in time. So if we start to talk about some state, it's important that you know to which picture does the state belong. And from now on, we're going to have to actually spell out what picture the state belongs to. So for all of these Schrodinger picture states, I'm going to put a subscript S. And I put a subscript S here in red just to stress that now we have got Schrodinger picture states everywhere. So we're going to have to distinguish between Schrodinger picture states and Heisenberg picture states. So in the Heisenberg picture, if I have some state psi of t, and there's a little h for Heisenberg picture, this will be exactly the same as psi of naught, because the states simply do not evolve. Now, I'm going to need to connect Schrodinger and Heisenberg picture in some way. So how do I connect these two pictures? Well, one of the equations that I specify to say how the two pictures are connected is that I say at t is equal to 0, the Heisenberg picture state and the Schrodinger picture state actually agree. Okay, so the Heisenberg picture state at time 0 is the same as the Schrodinger picture state at time is 0. Away from time is 0, the two will not agree, and they won't agree because the Schrodinger picture state evolves, whereas the Heisenberg picture state doesn't. Good. Let's now start to talk about operators. Again, I'm going to have to start telling you where the operators come from, because in the Schrodinger picture, operators didn't evolve in time. So this was a Schrodinger picture operator position, Schrodinger picture operator for position. And this operator at time t is the same as the operator at time naught, and the same thing for momentum, and the same thing for this general operator S that I have defined. In the Schrodinger picture, in the Heisenberg picture, the operator OH at time t is not equal to the operator at time 0. Let me tell you how they are related. It's e to the I ht. If I was putting in h bars, I would have divided by h bar, but I'm not putting the h bars in anymore. Then I would have the Heisenberg picture at naught and e to the minus I ht. So this would be the time evolution of the Heisenberg operator. The other statement I must make to say how Schrodinger and Heisenberg pictures are related is that the Schrodinger picture at time naught is equal to the Heisenberg operator at time naught. So the Schrodinger operator at time naught is equal to the Heisenberg operator at time naught, and this will be true for any operator that you choose to think about, just the same way that the evolution equation that we write down for O above is a general evolution for any operator. Okay, let's just hammer the point home. The Heisenberg operator for position at time t is e to the I ht, the Heisenberg picture operator at time naught, and e to the minus I ht. Good. So now I've told you what the Heisenberg picture is. You've seen how the operators and states evolve. One question that you might ask yourself is, how do we know that the Schrodinger picture and Heisenberg pictures will agree in all of their predictions? Well, let's try to check that. So let's start off with phi of t in the Heisenberg picture, the Heisenberg operator at time t, and then another state, Heisenberg state, psi of t. Okay. So let's now just start to rewrite this with what we know, okay? So we know that the Heisenberg state at time t is equal to the Heisenberg state at time 0. So this is equal to that, okay? Then the Heisenberg operator at time t is e to the I h t. The Heisenberg operator at time 0 and e to the minus I h t. So I have just used the known time evolution for the Heisenberg operator. And then psi of t, Heisenberg state, is equal to psi of naught, Heisenberg state. So I've just used the time evolution for the Heisenberg state. Good. Now, I'm going to use the fact that I know how the pictures are related. You see, I've written all of the states at time 0, all of the operators at time 0, but at time 0, I know that Heisenberg picture states are equal to Schrodinger picture states, and Heisenberg picture operators are equal to Schrodinger picture operators. So this will be equal to the Schrodinger picture state, phi of naught, e to the I h t. This is the Schrodinger picture operator at 0, then e to the minus I h t, and then Schrodinger picture state at time 0. And now I'm going to think about my Schrodinger picture time evolutions. In particular, e to the I h t acting on the bra at naught will produce the bra at time t. That's how our bras transform in the Schrodinger picture. So this is nothing but the Schrodinger picture bra phi of t. Then next, I know that Schrodinger picture operators do not evolve with time. So OS of naught is equal to OS of t. And then finally, e to the minus I h t on ket psi of naught, well, this is just the time evolution for the Schrodinger ket. So this is going to turn us into psi of t at time s. So I have just recognized the time evolution of the Schrodinger picture ket. And what you notice here is that we said that every physical quantity can be expressed as some bra, some operator, some ket. You notice that the Heisenberg picture bra phi, Heisenberg operator OH, Heisenberg ket psi at time t, all at time t is equal to Schrodinger picture bra phi, Schrodinger operator O, Schrodinger ket psi, all at time t. So this calculation that we just did here, this proves to us that every single physical prediction of the Schrodinger picture agrees with every single physical prediction of the Heisenberg picture. So the two pictures are in perfect agreement, okay? This is the proof that the two pictures are completely equivalent. Very good. So this red equation is really important because it's the proof that the two pictures are equivalent. Now, there are not just two pictures in quantum mechanics. There's many more than two pictures in quantum mechanics. For example, you might have met something called the interaction picture. In the interaction picture, the operators evolve according to the free dynamics, but the states evolve according to the interaction. So the states only evolve when our particles are interacting, and the interaction picture is a wonderful way to define the S matrix of a system. So the interaction picture is also known as the Dirac picture. So there are other pictures of quantum mechanics. What are we doing here? Well, we want to move away from states. Remember how complicated our Fock space state was? And we want to start focusing on the operators. So we would like a situation where the states don't have the dynamics, but the operators do have the dynamics. And that is Heisenberg picture. So from now on, we work in Heisenberg picture. And that's so that we are focusing on the operators and not on the states. Great. We'll continue in a moment.